Hello, this is Obstructing Lagrangian Concordance for Closures of Three Braids, Part 1. Thank you to the organizers for the invitation to speak. We're going to start with the definition of Lagrangian concordance. So this follows from Chantrain. Let lambda minus and lambda plus be Legendrian knots in the standard contact R3. Then a Lagrangian cobordism from lambda minus to lambda plus is an embedded Lagrangian surface, L in R4, such that these two equations hold for some t greater than 0. So what these two equations say is that there's some t such that, beyond that t, this Lagrangian has cylindrical ends. And between minus t and t, we can have some interesting things happen, some genus, what have you. Now, a Lagrangian concordance is just a genus 0 Lagrangian cobordism. So if a Lagrangian cobordism has genus 0, then it is what we call a Lagrangian concordance. And if there is a Lagrangian concordance from lambda minus to lambda plus, then we say lambda minus is Lagrangian concordant to lambda plus, and we write lambda minus is concordant to lambda plus using this inequality symbol. Now we can ask sort of a basic question, which is which Legendrians, lambda minus and lambda plus, satisfy lambda minus is concordant to lambda plus? And it turns out the answer is, well, Legendrian isotopic Legendrians satisfy concordance, and this was proved by Chantrain. It's also the case that concordance is reflexive and transitive, but it is not symmetric. And this also follows from work of Chantrain, where he shows that, for instance, or in particular rather, the unknot is concordant to the following Legendrian knot. Okay, I think I did it right. And this is the mirror of 946. So basically what he does is he constructs a concordance from the unknot to this knot and proves that there's no concordance in the other direction. And so concordance is not symmetric. So if it's not symmetric, the natural question might be, is it anti-symmetric? I.e., if lambda 1 is concordant to lambda 2 is concordant to lambda 1, does that necessarily mean that lambda 1 is Legendrian isotopic to lambda 2? Or, phrased another way, this is like asking, is concordance a partial order on Legendrian knots? Turns out the answer is that we don't know, and this is quite a difficult question to ask or answer. So we might ask a simpler question. So if U is the maximum Thurston-Banachkin number Legendrian unknot, if U is concordant to lambda is concordant to U, then does that mean that lambda is the unknot? So let's just throw away all of the Legendrian knots and just look at the unknot case and ask, is it true that the unknot case is anti-symmetric? Turns out the answer is, again, that we don't know, and this is quite a difficult question to answer, but there is some progress. So we have some known obstructions. So the first obstruction is that we know that lambda must be quasi-positive, and this follows from work of Boileau and Revkov, which says that if a knot can be filled by a Lagrangian disk, then it has to be quasi-positive. And we can see this Lagrangian disk because we know that the unknot can be filled with a Lagrangian disk. So if we just fill the unknot with a Lagrangian disk, then if we glue the cylinder and this disk together, we get a disk, which is Lagrangian. Now this Lagrangian disk is also smoothly a disk, so lambda must be smoothly sliced, meaning that we can use all of the topological obstructions from smooth sliceness. Another obstruction is that we know that the Thurston-Banachkin number is preserved by concordance. So in this case, we know that lambda must have TB minus 1. This follows from Chantrain. And then we get a whole bunch more obstructions from Cornwell, Ing, and Seebeck, who show, for instance, that lambda can't be alternating, that if we have concordance between two knots, then we have concordance between their satellites, and also that if this is a decomposable concordance, then lambda has to be U. So the result that I'm showing you today is another abstraction to concordance, or to double concordance, and it's the following theorem. So if lambda satisfies U is concordant to lambda is concordant to U, and lambda is smoothly the closure of a 3 braid, then lambda is Legendre isotopic to U. So the strategy in order to prove this is going to be, so first let's consider, instead of lambda and U in R3, let's just consider lambda and U in S3. And what we're going to do is we're going to do a slight perturbation, so a little wiggle, so that the Legendrian knots are now transverse knots, and the Lagrangian cylinder between them is now a symplectic cylinder. And now what we can do with this new picture with transverse knots and symplectic cylinders is to take double covers of everything. So double covers of S3 branched over these transverse knots, and double cover of the ambient space branched over the symplectic cylinder. And we're going to obstruct this cobordism between the double covers instead of obstructing the concordance between the knots themselves. So this is what we're going to show cannot happen. Okay, so you might wonder why 3 braids? Like, why is this a hypothesis in the theorem? And the answer is comes in 2 bullet points. The first thing is that any quasi-positive Legendrian lambda has a transverse push-off lambda prime of the same smooth knot type. And transversely isotopic, this transverse push-off is going to be transversely isotopic to a transverse quasi-positive braid of minimal index. And this follows from work of Hayden. So basically, if I want to think about quasi-positive Legendrians, I can think about quasi-positive transverse knots. And these things are very braidy. And the second reason is because of a famous result of Murasugi, which says that any 3 braid is equivalent up to conjugation to one of the following 3 words. And what this means is that if I want to obstruct 3 braids, all I really have to do is make sure I obstruct every braid that I've listed. And once I've obstructed everything that I've listed, or that's listed here, then I've obstructed everything, so we're done. Okay, so now for the rest of the talk, I'm going to give you the proof of this theorem. So this proof is going to come to you in 3 parts, mainly. The first part is that we're going to show that if lambda is the closure of a 3 braid beta, satisfying U is concordant to lambda is concordant to U, then beta has to have algebraic length 2. So this is a restriction on which braid words we're looking at. So we're going to eliminate a bunch of the braid words, and with the remaining braid words, we're going to proceed to part 2, where we draw the Weinstein diagram of a filling x lambda of the double cover branched over lambda using an open book decomposition, which comes from the braid word beta. Okay, so now that we have this Weinstein diagram of a filling of the double cover, we can move on to part 3, where we'll use this Weinstein diagram to compute differential graded algebra. And we'll use this DGA of the attaching spheres in the Weinstein diagram to show that the symplectic homology of x lambda, the filling, is non-zero. So this is roughly the structure of the proof. and we're going to end up in a contradiction. So let's start with part one. So first thing we're going to do is throw out a bunch of braids that we don't need. So first we're going to eliminate braids of Murasugi type 2 and type 3. So type 2 braids look like this. And the reason why we can throw them all out is the following. So these braids are going to consist of some number of full twists of all 3 strands, followed by some number of full twists of the last 2 strands. So the braids are all going to look something like this. I'm not drawing the crossing information just because this works if it's a positive or a negative full twist. So here is a full twist, and here is, some number of full twists on the latter 2 strands. Now what I'm going to do is I'm going to take a look at this first strand, and I see that if I trace this first strand, when I close up the braid, it's going to form its own component in this link, which means that all of the braids of Murasugi type 2 correspond to multiple component links, so not knots, so they can't be concordant to the unknot. All right, so that was pretty straightforward, and braids of Murasugi type 3 are also fairly straightforward. So the way we're going to do this is we're going to first take a look at if D is less than 0. Well, if D is less than 0, then this braid is negative, meaning that all of the generators forming the braid word have negative exponents. And if you'll remember, one of our first obstructions is that the braid has to be quasi-positive, so we can definitely throw out all of these. Now, sorry, this is less than or equal to 0. Now, if D is equal to 1 and K is equal to minus 3, then this is the unknot. So let's not worry about this case. And if D is greater than 0 otherwise, what we can do is we can perform a series of word manipulations to the braid word. So up to equivalence, these braid words are going to be positive. Now there's a result from Kronenheimer and Rufka, which says that if a braid is smoothly sliced, then it cannot be strongly quasi-positive. And braids which are positive are strongly quasi-positive. So none of these can be smoothly sliced, so we can throw them all out as well. So what we're left with is just the unknot and the Murasugi type 1 braids. So to deal with the Murasugi type 1 braids, we're going to need a little bit more work. And in particular, we're going to first need this lemma. So this lemma, which I'm calling lemma A, says that if lambda satisfies U is concordant to lambda is concordant to U, then any p-fold cover, sigma p of lambda, of S3 branched over the transverse push-off lambda prime of lambda must embed as a contact type hypersurface in the 4-ball. The way that this is proved is basically by like an explicit construction of this embedding. It's going to consist of this sort of filling component and this other piece, which I'm going to call V because it's actually going to come back later. And this is going to be a 4-ball. Okay, so once we know that the double cover of lambda embeds in the 4-ball, or any p-fold cover embeds in the 4-ball, we're going to use this by considering the following invariant. So this is Gompf's D3 invariant of plane fields. So if we have a contact manifold and an almost complex manifold, 4-manifold, for which the contact manifold is the boundary and for which the contact structure is compatible with the almost contact structure, then letting sigma be the signature of X and chi being the Euler characteristic, we get that D3 can be computed by this formula. And if we take X to be the filling of sigma 2 lambda, which embeds in R4 in the construction of the previous lemma, then we can compute the D3, and we get that D3 is of these contact manifolds is minus a half. Now the D3 invariant can also be computed using information about the knot itself. So in particular for the case where we have a branch double covering. So another formula for D3, where M is the contact branch double covering of S3, of the standard S3 branched along a length K, then by work of Ito, it's given by the following formula in terms of sigma, which is going to be equal to the Murasugi signature and the self-linking number. So the Murasugi signature can also be written in terms of the 3 braid words, and this is given by a formula of Earls for 3 braids of Murasugi type 1, 2, and 3, but for in particular in our case for Murasugi type 1 braids. So if we combine all of these things together, we get the following restriction on the braid word. So if lambda is of Murasugi type 1, then we know that the sum of the exponents has to be n plus 4. Either that or lambda is the n-naught. And in either of these two cases, we can compute that lambda has algebraic length equal to 2. So this finishes up the proof of the first part of the theorem. Okay, so we're gonna start taking a look at the proof of the second part, and then I'm going to end this part of the video, and the rest of the proof will be in the second half. So in part 2, the main theorem that we're going to be proving is that if lambda is not the unknot and is the closure of a quasi-positive 3 braid of algebraic length 2, then the double cover of lambda has to have, the double cover of the transverse push-off of lambda has to have a filling, which we'll call X lambda, and X lambda has Weinstein handle decomposition given by this diagram. So this diagram consists of one handle and one two handle. So the green and blue shaded regions are one knot, and the shading just means some number of parallel strands. So some number of over-crossing strands in the green regions, which are all parallel, and some number of under-crossing strands in the blue region, which are all parallel. And so the first step of the proof of this theorem is going to be to use beta to construct a particular open book decomposition. So step 1, since lambda is the closure of a quasi-positive braid with algebraic length 2, beta is equivalent up to conjugacy to the braid of the form sigma 1 b, sigma 1 b inverse, where b is just some braid. Now this can be achieved by basically taking the braid and performing the right number of conjugations by sigma 1 or sigma 2, and this will we can always do this to manipulate the braid word so that it takes this form. Now for the rest of the talk, I'm going to be using the following knot as a running example. So the tan 155 knot is doubly smoothly sliced, and we're going to go through the process explicitly with this knot, and this will show that it's not doubly Lagrangian slice. But also because I don't really want to draw things out in generality in this talk, I think it's easier to understand what's going on if there's an explicit example. So in the case of the 10-155 knot, this can be written as the following braid word, taking the form sigma 1 b, sigma 1 b inverse. Okay, so from this braid, we're going to construct an open book decomposition. So the open book decomposition of sigma 2 lambda is going to have contact structure, so the contact structure will be compatible with the open book F phi, where F is going to be a punctured torus, and phi is going to be given by Dane twist corresponding to the braid word. In the following way, if I have a sigma 1, then that's going to be Dane twist about the curve alpha pictured here. And if I have a sigma 2, that's going to correspond to a Dane twist about beta pictured here in this punctured torus. So how does this work? It comes from an idea of Planinevskaya. So the idea is that we're going to start with a planar open book decomposition of S3 with monodromy given by beta in these sort of half twists. And then what we're going to do is we're going to take the double cover of each page. And when we do this, the double cover of each page is going to be a punctured torus. My half twists are going to become Dane twists. And what I get is an open book decomposition of the double cover of S3 branched over the braid beta, or branched over the closure of the braid beta, which is lambda prime. Okay, so let's say explicitly in our example, the monodromy of the open book is going to correspond to Dane twists about a particular curve alpha, or B curve alpha, and some particular curve gamma of slope P over Q with 0 is less than P is less than Q. We can guarantee this by, again, performing conjugations by sigma 1 to the braid word. And for example, in the case of the tan 155 knot, we have sigma 1, the first letter in the braid word, which gives us a Dane twist about alpha. And then the rest of the braid, which is this B sigma 1 B inverse, is going to correspond to a Dane twist about this curve, which we'll call gamma. And this is a curve with slope 2 over 5. All right, so given any knot lambda, which is quasi-positive and of algebraic length 2, I can do this and always obtain some open book decomposition, monodromy given by alpha, the same alpha every time, and some gamma of slope P over Q. Okay, and so to see what's going to happen to this open book decomposition, please join me in part 2 of this talk.